Welcome back. Uh, we are going to be covering spectroscopy and spectrometry in the next sections of the course. I am wearing another fun Hawaiian shirt. So, for this chapter, for chapter 14, it's chapter 13 and older editions of the book, we're going to be talking about mass spectrometry, infrared spectroscopy, and ultraviolet/visible spectroscopy. Now, uh, I used to be confused on what makes it spectroscopy versus spectrometry. Key thing is it's using light. If we're measuring the absorbance and the transmission of light, any kind of light, that could be visible light, it could be microwave light, you name it, then it is spectroscopy. Mass spec does not use light, and therefore it is spectrometry. We're measuring the mass of compounds in mass spec. So what are we going to get from these different sections? For mass spec, the key thing that we're going to get is the molecular formula. We will also get fragmentation, that's helpful, but the molecular formula is the key thing that we're, as organic chemists, going to get from mass spec. In IR, we're going to learn about the functional groups that are in the molecule. And importantly, as I have shown here, we'll learn about functional groups in the molecule and functional groups that are not in the molecule. Both of those are extremely important. So with IR, we're basically, I like to think of it as puzzle pieces. We're finding out what puzzle pieces are in the puzzle. Do we have a carbonyl? Do we have an alcohol? Do we have an alkyne? Do we have a nitrile? Do we have a carboxylic acid? Right? Each of those are different puzzle pieces that would be part of our molecule. And as I show here, equally important is, do we not have a carbonyl? If we don't have a carbonyl, oh, well then we must have something else. And then the UV-Vis, so ultraviolet/visible spectroscopy, deals with pi bonds and in particular conjugated pi bonds in the system. Okay, this is just a reminder of the different functional groups. I will be referring to ethers and alcohols and ketones and carbonyls. All of these C double bond O's, those are all carbonyls and they're different flavors of carbonyls. So make sure you're familiar. And then the other one that we haven't really talked too much about is an aromatic ring. So when you have these benzene rings, we'll occasionally be talking about that, especially when we get to NMR. Okay, so familiarize yourself. In mass spectrometry, what the mass spec is able to identify is always some sort of ion. The book tends to talk about that it needs to be positively charged. Today's mass specs can operate in either positive or negative mode. In the book, it talks about using this electron beam. Again, today's mass spec doesn't use typically this to ionize the system. A lot of times we will protonate or deprotonate compounds. There are plenty that do use an electron beam, but realize what we're going to be covering in mass spec is just the service kind of introductory level of mass spec. But importantly, this is true, all mass specs, all that they can identify are ions. Whether they be positively charged or negatively charged, they need to be ions, they need to be charged. Okay, so how does this work? What happens is you take your sample, somehow get it into the mass spec. There's a whole area of mass spectrometry people that are focused on getting it into the mass spec, always in the gas phase. Once it gets in, it becomes ionized. So in this part of this mass spec this is the electron beam that will ionize the system. It goes through these plates to kind of focus the beam, and then it goes through this tube. This is the tube that's under vacuum, meaning there's no other molecules to bump into. And what happens is this thing shoots the molecule, and as it goes here, if it wasn't for this magnet, it would just pink into the side of the tube. But instead, there's this magnet here that applies a magnetic force to it, so that it's attracted to that magnet. And therefore, as it goes, the heavier molecules feel that magnetic force less and are over on this side of the beam. The lighter molecules are more affected by that magnetic field and are going to be more on this side. So what you do is you adjust the magnetic field to get different molecules through the slit to get to the detector. So what happens is you ionize it and then it bends it, and depending on the mass of the compound, it will bend more or less. And that then tells you from the detector, you run controls, you run samples, and then you can figure out the mass of your compound. Now, as it goes through the mass spec, it will also what we call fragment. So we will not only get the parent molecule, but you also get little fragments of molecules as well. Now, in the mass spec, we are looking at individual molecules. We're not looking at the approximate mass of the molecules. You're looking at the mass of individual molecules. Now, if you look at your periodic table, you will notice that the masses are a little bit funky. So, for example, chlorine is 35.45. That does not mean that one atom of chlorine weighs 35.45 atomic mass units. It's either going to weigh 35 or, in this case, 37, because if you look at the different isotopes of chlorine, there's actually none of them that weigh 36. They're either going to weigh 35 or 37, depending on how many neutrons it has. Now, if you take the weighted average, so if you take 75% of 35 and 25% 37, suddenly you then get that, about 35 and a half. Likewise, bromine. If you look at bromine on the periodic table, it comes in at 79.9. So if you know that the periodic table is the weighted average of the masses, and you see the bromine's 79.9, you might think most of it is bromine 80. But in the end, there's no bromine 80. It's either half bromine 79 or half the chance likelihood that it's bromine 81. And because it's half and half, you take the weighted average and you get about 80, which is what the periodic table shows you. Now, another one that's important is carbon. So about 1% of carbon is carbon-13. That can tell you then how much carbon you have. So, for example, in the mass spec, you get the mass of your compound, and if something weighs 1 atomic mass unit heavier, then that will tell you how many carbon atoms if you take the ratio of that versus the normal peaks. If the normal peak height is, let's say, 100, and then the m+1 peak is 20% of that normal height, well, then you must have about 20 carbon atoms in the molecule, because 1% of the time that carbon will be carbon-13 and boosted forward. Likewise, if you have a large m+2 peak, that's going to suggest you either have a chlorine or bromine, right? Because chlorine is normally 35 or 37. Bromine is 79 or 81. Notice the M and the m+2 peak. And then a funky one is that an odd number for your mass indicates an odd number of nitrogens. So why is that? Because nitrogen weighs 14. So why would it be odd? It's because nitrogen likes to have 3 bonds to it. So if you take, for example, ammonia, so NH3, right? So nitrogen weighs 14, hydrogen weighs 1, that gives you 17. Likewise, if we take methylamine, so the carbon weighs 12, nitrogen weighs 14, and we've got 5 hydrogens. And let's see, we're looking at 6, 1, 31. Once again, an odd number. Now, 2 odds equals an even, right? So if you have an even number of nitrogens, well, then it ends up being an even number, and you don't know that you have nitrogens. But it's pretty rare that you have an odd number. So if you have an odd number, that's going to indicate you've got an odd number of nitrogens. Let's take a look at an example mass spec. So this is a mass spec. Now notice down here, M over Z. What that means is the mass divided by the charge. m over z. So for this class, the vast majority of compounds that we work with the z, or the charge, will be 1, right? And therefore, mass divided by 1 equals mass. So in the x-axis, this is going to be the mass. The y-axis is the relative abundance. What that means is how frequently that mass hit the mass detector. So the relative abundance doesn't matter too much. We'll get into where it comes into play, but it's not a huge thing. Now, for myself as an organic chemist, the most interesting part for me is on the far right of the mass spec, because this is going to be my parent ion peak. In this case, my mass for 1-bromopropane is going to be 122. But notice there's an M+2 peak that has equal intensity. Well, that's because half the time it's 122 because you've got bromine 79, that isotope, and half the time it's going to be 124 because you're using the bromine 81 isotope. So that's where I say the M and M+2, if they're equal height, you've got a bromine. This is an example. Now notice you can fragment off this bromine to leave behind a propyl cation at 43, and that's what that represents. If we go from bromine to chlorine, now all of a sudden your M and your M+2 go in a 3-to-1 ratio, because the abundance of chlorine 35 versus chlorine 37 is 3-to-1 ratio. It's 75% chlorine 35, just 25% chlorine 37. So when you have M and M+2, that's a 3-to-1 ratio. Well, that's a big hint that you've got chlorine in your molecule. Once again, if you fragment here, you get that propyl cation that has a mass of 43. All right, so this is the mass spec of pentane. Once again, M over Z for this class, we'll be dealing with singly charged molecules, therefore Z equals 1. So this is just simply the mass. Now, if you take pentane and fragment, cleave any of those carbon-carbon bonds, you will then get these different masses. Take a closer look at this. You can fragment, here to get these two masses. Now notice the radical, we're not observing that. I don't care what the mass of that is because I can't see it. It needs to be a charged species to be observed by mass spec. So these are the 4 charged species that I would see, and those are the species we saw in the mass spec on the last slide. Now if you compare 2 different isomers, so this is pentane, the mass spec we were just looking at, and this is isopentane, also known as 2-methylbutane. And as you can see, they both have a mass of 72. But notice the height of this peak at 57 is a lot larger here. This peak at 57 comes from a loss of a methyl group. So if we fragment this methyl group, fragment this methyl group, or fragment that one, if you do any one of those fragmentations, you're going to get a mass of 57. On this case, if you fragment here or you fragment here, you get that peak at 57. Now, why is this one so much larger? It's because if you cleave this bond or if you cleave this bond, you leave behind a secondary carbocation. Secondary carbocation is better than a primary carbocation, and because of that stability, it will fragment much more frequently than in this case. So that's where the relative abundance, so the y-axis, can come into play. Now, I will never ask you what is the mass spec for isopentane. For one, I'll never call it isopentane. I might say, 2-methylbutane, but I'm not going to ask for the mass spec. Now, I might ask, what are some fragmentations that you would observe? I might say, what are 4 fragmentations that you would observe? So or 4 masses, I would say. The parent ion, and then fragmenting here, fragmenting here, fragmenting here, right? All of those fragments will give you masses. So what's another example of a question that I would give? So I might say, how can you identify between these 2 different molecules? Now, both of these molecules have the same mass, right? They're both C6, 1, 2, 3, 4, 5, 6, 1, 2, 3, 4, 5, 6. Yep. And if it's C6, it will then be 14. You can go through and count your protons, and hopefully I've got it right. So I'm looking at 6, 7, 14, perfect. All right. Now I can fragment off a methyl group. Let's go with purple. So I can fragment a methyl group, 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 methyl, methyl, methyl. So all of these purple are going to be the parent ion minus a methyl, and then we would also see the methyl peak. So to figure out what the mass is, let's first look at the parent peak. So the mass is going to be, so carbon weighs 12, 12 times 6 plus 1 times 14, because there's 14 hydrogens. So this is 72 plus 14, so this gives us 86. Right, so both of these will have masses of 86. And then if we lose a methyl group, so a methyl group is a CH3, so that's 15, right? Because CH3, C, so a carbon is 12, plus 3 hydrogens is 15. So we would get the peak of 15 on both of them, because we can fragment a methyl group on both of them. But we would also get minus 15 from 86, so 71. We would have that peak, that mass for both of them. And let's I don't know if you can see that well, but the circled in purple are from breaking those bonds. Now let's go in red. So the only bond we have left to cleave here would be that one. So that would cleave off a propyl group. And we can do that here as well. So then a propyl group is a C3H7, right? The way I got that is I took the mass. If you cleave this bond, that is C3H7. C3H7, so 3 times 12 is 36, plus 7 is 43. So both of these would have a mass of 43. Now in this case, I say it has a mass of 43. Usually you look at on either side, but on both sides it's a propyl group. So that doesn't do anything different. And then the last one is you can fragment right here. So if you do that, you're going to have an ethyl group on one side and a butyl group on the other side. Now there's no way with the molecule on the left that you can fragment off an ethyl group or a C2H5. Right? So in this case, on the right one, you would have a mass of that ethyl group. So C2H5, what did I say? So that's 12, 17. So we would have a mass of 17. Nope, that's a lie. 24 plus 5 is 29. I'm sorry, that sounds a lot better. You would have a mass of 29 for the ethyl group, and then you would have a mass of 57. So that's 86 minus 29, 57. So you would have these extra masses for the right molecule. So how does this tie into what I might ask on a quiz or exam? On a quiz or exam, I might say, what are two masses that would help distinguish which of these isomers you have? Right, and then you got to go through and think about which fragmentations can happen on the right versus the left, and hopefully there's some that happen on one, not the other. So, all right, so with that, I'm going to stop this video, and the next video will continue with more advanced fragmentations using mass spectrometry.